Now let's continue with Chapter 17 on aromatic compounds. And we're going to look now at aromatic compounds other than benzene and some of the reactions of benzene. Reactions at the benzylic position, which is a special position because intermediates at that position can be stabilized through resonance with the benzene ring, and reduction of benzene and its derivatives. So we're going to cover sections 5, 6, and 7. So as we discussed earlier, aromatic compounds fulfill these two criteria, which I've already discussed at great length. And aromatic compounds fulfill anti-aromatic compounds fulfill the two criteria. A fully conjugated ring with overlapping p orbitals and an even number of electron pairs. So the difference is an odd number of electron pairs in aromatic compounds and an even number in anti-aromatic compounds. Both, whether it's aromatic or anti-aromatic, it's required to have a fully conjugated ring with overlapping p orbitals. Annulenes, these are rings that are fully conjugated. The name for this is 6-annuline, notice 6 carbons, 10-annuline, 10 sp2 hybridized carbons in a ring, and 14-annuline. This is 14 sp2 hybridized carbons in a ring in conjugation. So annulines, though, could be aromatic, anti-aromatic, or non-aromatic. In order to be aromatic or anti-aromatic, the rings must be planar. So it is possible that these rings can sort of fold or disorient enough so that they lose their planarity, and that is how they could become non-aromatic. Aromatic rings can contain carbanions or carbocations, considered the 5-membered ring. Here you have 3 bonding molecular orbitals that can accommodate 6 pi electrons. If it does indeed have 6 pi electrons in this 5-membered ring, it would be aromatic, and that would be cyclopentadienyl anion, which is shown here. And you can see that that negative charge rotates all the way around the ring by using its resonance structures, so it is very much stabilized, and it is aromatic. The cyclopentadiene is more stable, or more acidic, rather, than organic compounds typically are, because when the proton is removed, it leads to an aromatic anion, as shown up here. So this structure has 2, 4, 6 pi electrons in a ring. So you don't have to have 6 carbons. The aromaticity depends on the electrons, not the number of carbons or the number of nuclei. And so the pKa of 16 is an unusually low pKa for an organic compound. Think back on, say, propane or ethane, which have a pKa of about 50. That's 50, as compared to this one, which is 16. And so that's this is unusually acidic for an organic compound. Now, another one. This is a 7-membered ring. And you can see that it has 1, 2, 3 bonding molecular orbitals, which can contain 6 pi electrons. So it's the same situation that we saw before. It doesn't matter how many nuclei it has, the molecule has. It only matters how many electrons it has. And so if this one has 6 pi electrons, 2, 4, 6, it will be aromatic, and this will be a cyclic cation. And you can see that the cation, the positive charge, can rotate all the way around the ring by using all of the different resonance structures. This particular cation is aromatic, and it is called tropylium. This is the tropylium cation. Or you can just say cycloheptatriene cation. Heteroatoms also can be in aromatic compounds. So now you see these two molecules. These are nitrogen containing. And so this one is pyridine, this is pyrrole. You see this is aromatic, 2, 4, 6 pi electrons. You do have a non-bonding pair on nitrogen, but this pair of electrons is orthogonal to the ring. This pair of electrons is not needed to achieve aromaticity. This pair of electrons is not involved in the aromatic ring. It lies in an sp2 hybridized orbital. Now, pyrrole, you have a pair of electrons on nitrogen, and this pair of electrons occupies a p orbital, because if you use the pair of electrons on nitrogen, that's 1, 2, 3 pairs of electrons, and that is what is needed for aromaticity. And so this pair of electrons on nitrogen is needed for aromaticity. Over here on pyridine, this pair of electrons is not needed for aromaticity. Here, this one on the nitrogen in pyrrole, the pair of electrons is in a p orbital and in conjugation with the other p orbitals. And so you have 6 pi electrons, 3 pairs circulating in a pi cloud. So this really just states what I just said, but it's demonstrated that if you protonate the pyridine, you can see that this molecule, the conjugate acid, the cation that's formed, is still aromatic. And so it has a pKa of 5.2. Now, if you protonate pyrrole, it will tie up the pair of electrons on nitrogen. And remember, we said that this pair of electrons is needed for aromaticity. And so now, in the cation that's formed, the aromaticity is broken up. It's removed because you only have 4 pi electrons in conjugation now. And so this system is going to lie far to the left. It will have a great tendency to give up this proton so that it can achieve aromaticity again, and that is reflected by a very low pKa, and so of 0.4. So this compound, protonated, is non-aromatic. The other 3 structures on this side, on this slide, are still aromatic. Now you can see the electron density maps, the electrostatic potential maps. Here is nitrogen. You can see the pair of electrons on nitrogen is sort of localized on nitrogen because it's not involved in the pi ring. But on pyrrole, you can see the pair of electrons on nitrogen is delocalized throughout the pi ring because that pair of electrons is needed for the aromaticity. So you can see the red is spread out through the ring. So it's the red that designates the high electron density. Polycyclic aromatic compounds. So these are also aromatic. Notice that you have 1, 2, 3, 4, 5 pairs of electrons in the ring. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Those are all odd numbers. So these are expected to be aromatic, and indeed they are. You can see the stabilization energy here is quite high. The stabilization energy per ring, because benzene has 1 ring, naphthalene has 2, anthracene and phenanthrene each have 3, and so this is the stabilization energy per ring. This is the stabilization energy of the entire molecule. And so you can see anthracene, in the case of anthracene, it has a low stabilization energy per ring, and it is known that when anthracene reacts, it reacts across here at these 2 positions in order to give 2 intact and isolated benzene rings. And so the stabilization energy on this molecule is less. The carbon directly attached to a benzene ring, this is called a benzylic position, regardless of how many, whether it's a primary, secondary, tertiary carbon, it doesn't matter. It's still called a benzylic position. This is a benzylic position. And they're more reactive than might be expected. So here, if you have unsubstituted benzene with sodium dichromate or heptane, there's no reaction with that set of reagents. However, for the benzylic position, it does react. Whatever is on here, it doesn't matter if it's a methyl, or here it's shown a butyl, it doesn't matter if it's a hexyl, it doesn't matter what is there, so long as there is 1 proton at that position that can be removed to start the reaction. You must have 1 proton at the benzylic position so that it can be removed and the reaction starts. And then whatever else is on the benzylic carbon just gets removed, because this is a very strong oxidizing agent, and so the rest of this just gets removed. 1 carbon is left attached, and it is fully oxidized, okay? Because this is a very strong oxidant. If the benzylic position does not have 1 proton attached, then it does not react. The reaction cannot be initiated. It's the same way with potassium permanganate. At the benzylic position, if there is 1 proton, at least 1 proton there, that carbon at the benzylic position will be fully oxidized, and the remaining atoms attached to it will just be lost. So regardless of which oxidizing agent is used, the reaction is the same. Benzylic positions are highly active. So for example, in radical reactions, so a radical will be formed at this benzylic position. So whether you have a radical or a cation or even an anion, whatever the situation is, that that unpaired electron or that charge can be stabilized by conjugation inside the ring. And so that's why you see these reactions at the benzylic position. So N-bromosuccinimide and heat is used to brominate at the benzylic position. So whatever the reactive intermediate is, whether it is a cation, anion, or radical, it will be stabilized if the reactive intermediate is at the benzylic position, the charge or the unpaired electron. So an SN1 reaction, you remember what an SN1 reaction is? Loss of bromide. A cation will be generated here. That cation at the benzylic position, the positive charge can be stabilized by conjugation throughout the ring. In an SN2 reaction, hydroxide comes in and displaces the bromide. In the SN2 reaction, at the benzylic position, and that will be stabilized also because the transition state structure that this goes through will be in conjugation with the electrons in the ring. Similarly, E1 or E2 elimination will be facile because when the pi bond is formed, that pi bond is in conjugation with the ring. And so these reactions are facilitated by conjugation with the benzene ring. So notice this, again, is at the benzylic position. So being at the benzylic position facilitates all four of those reactions, SN1, SN2, E1, E2. So this is a summary slide of the reactions that we've discussed. So you can see the radical bromination, the oxidation at the benzylic position, SN1 and SN2. Here, SN1, E1 or E2 to give the double bond that is in conjugation with the benzene ring. And so this is a nice review slide that is in your text in section 17.6. And it would be very useful to go over this and ensure that you know these reactions because they're all important reactions. Benzene can be reduced to cyclohexane, but it is a very high energy process. So one must have a catalyst 100 atmospheres, 150 degrees centigrade. However, if you only want to reduce the carbon-carbon double bond, exocyclic double bond, in the presence of benzene and leave the benzene ring intact, that's possible also. Just use milder conditions. It's still catalytic hydrogenation. Benzene can also be reduced in an unusual reaction called the Birch reduction, where the two positions that are reduced are para to each other. So these are at the 1,4 positions. And it's an unusual, somewhat unusual reaction. It goes through a radical anion, actually. So remember, this is in the presence of sodium metal. So see, you have sodium metal, methanol, and ammonia. And so the sodium donates donates a single electron to this carbon, forming a pair of electrons that it constitutes a negative charge. You push these single electrons down to form the double bond, and you have an unpaired electron down here. This negative charge plucks a proton off of the methanol, and so now you have a radical. So you've gone through a neutral molecule, through a radical anion, and now into a radical, which is at the 4 position to the CH bond that was just formed. And now we go on, the sodium metal donates a second single electron to form another negative charge, which again abstracts a proton from methanol. And so this puts the two new CH bonds at the 1 and 4 position. So that's the Birch reduction. It doesn't completely reduce the entire benzene ring, only the 1 and 4 position. And so now these are sp3 hybridized carbons. The presence of an electron donating alkyl group means that that alkyl group will be attached to one of the double bonds in the product. This is because the alkyl groups are electron donating. And remember that the more highly substituted a pi bond is, the more stable it is. And so this is the more stable pi bond that has the electron donating substituent attached to it. However, if this substituent is electron withdrawing, when the Birch reduction takes place, then the electron withdrawing group will not be attached to the one of the pi bonds, because the pi bond is less stable if it has the electron withdrawing group attached. So this is the product with the electron withdrawing group not attached to the one of the pi bonds. So that concludes the first chapter on reactions of benzene. So this is the first chapter on reactions of aromatic compounds, and the next chapter will also include many more reactions of aromatic compounds. So chapter 17 and 18 form sort of a 2-chapter set, and it will be really necessary to remember what you saw in chapter 17 while we're going through chapter 18.